Hey folks, today we'll look into a topic called Ensemble Learning. Basically what it does is it's a combination of multiple models, the machine learning models, right? So let's say some take a singular model, they think it's not working well, they take another model, it doesn't work well. So having a combination is kind of what this classification methodology does, right? So as you can see from the picture, you input any data, it runs through multiple models, does a combination and gives you an output and classifies data based on that, right? So that's basically the objective of it. There are a couple of methods in this. Let's talk about bagging, which is going to be an example of random forest. We'll talk about random forest in the next slide. Then there's a boosting methodology. Again, we'll be talking about gradient boosting methodology in the upcoming slides. And then there's stacking, which is another method of stacking multiple models and predicting an output or classifying the data into an output, right? So let's talk about the first one, which is bagging, which is random forest. So basically what happens in random forest is you have this original data, right? A data set of, let's say an example, numbers 1 through 10, right? Now what you do is you take that original data and create some samples. So you can create say 5 samples. So sample number 1 will be 1, 2, sample number 2 will be 3, 4, and so on and so forth, right? Based on that, then you build decision trees, which are random trees created. And then those random trees, as you all know, decision trees will give you a prediction. It will give you an outcome, right? And then that is given to a hard voting decision making. So hard voting is nothing but whichever has the majority, you kind of call that as the winner, right? So over here, voting class A is 2, so you give that as a final, right? So that's random forest basically. The other methodology is gradient boosting, which is more advanced, right? The reason why we say it's advanced is because gradient boosting, what it does is it does the initial prediction, very similar to what you saw in the random forest. But then what it does is it does another iteration. It builds residuals, right? Residual is nothing but error y minus y hat, right? We all know that. So basically it takes that and then using that, it builds another model, right? And then it keeps on doing that till we think that the model is really great. So it keeps on updating the predictions based on what is learned from the residual. And then there's also a parameter called learning rate, right? Let's take a numerical example to look into this. Let's say an example, this is your data, right? Your training data, which has X features and Y is your outcome, right? So basically what happens here is it does an initial prediction, right? Which is X is your feature set and the actual values, which is 7, 10, 5, 9, and 12. What you do is we do a prediction here, right? So here F0 is nothing but 8.6. So that's assumption of a prediction that you're doing. So you put that as a prediction value. So then what happens is you do a actual minus prediction, which is your residual, like we spoke in the earlier slide, y minus y hat, so which is 7 minus 8.6 here, so which is minus 1.6. Likewise, you do the same for 10 minus 8.6 and 5 minus 8.6 and so on and so forth. You get all those values that you see over here, right? Then what happens is you see at the bottom of the slide, there's something called as a tree rules, right? So tree rules, basically what they do is they kind of give you the rules that you need to do step by step. So the first tree rule here says that if X value is less than or equal to 2, then you call H1 as minus 2.6. So you're kind of putting some rules over there. And if X is greater than 2, then you make it 1.7, right? So the third box here, which says first week learner, where we are trying to predict the H1, the new prediction, right? And the learning rate N is 0.1 here. So that's why you see minus 2.6 gets converted 3 into N, which is the learning rate, as minus 0.26 because it's multiplied 0.1. Likewise, 1.7 has become 1.17, right? So that's how it happens. Now, the first week learner, basically what happens is it is multiplication of 8.6 into 0.26 minus 0.26, it becomes 8.34. So likewise, you do this new prediction, right? Now, it doesn't get over there. It doesn't, because as I said, it does a residual and keeps predicting till we want the final result, right? Then it does another prediction. So over here, you see there's a second tree rule given over here, right? So there's a second rule given here, So basically what it says is minus 1.2 if x is less than or equal to 3, and if x is greater than 3, then it's 1.8, right? So now you come here and do the tree, like the learning rate is 0.1. So you do this minus 1.2 multiplied by 0.1 gives you minus 0.12, and 0.18 likewise. And then you do the new prediction, which is multiplication of previous with this new prediction, gives you the new prediction, right? So that's basically a final result, right? Which is nothing but x, which is your actual training data, y, which is another actual training data that you had, and then the final prediction is nothing but your new prediction value is 8.22, 9.55, blah, blah. And then the final prediction is nothing but actual minus final, which is 7 minus 8.22, which is 1.22, and likewise, right? So that's how you do gradient boosting. So now let's move on to the next one, right? Even more advanced, which is nothing but XGBoost, right? Which is another advanced implementation of gradient boosting machines, again for optimization for speed, model performance, regularizations, to avoid overfittings and so on and so forth. So that's why we use XGBoost, right? So XGBoost, again, we use training data with some initial predictions like we saw in the previous slide. It builds sequential trees, right? So it builds tree 1, tree 2, tree 3. But in the previous one, what we saw, the relationship between tree 1 and tree 2 is random. You don't have a relationship there, right? But over here, as you could see, there are arrows here, right? So basically there's a sequential tree decision making, and then based on that you do predictions, you give weights to it, and then the weighted average gives you the final outcome. Again, let's look into numerical data here, right? So you have the training data here, the hours you study and what's the result going to look like. Fail, pass, fail, pass, fail, pass, and again you need to make it numerical, so you make it fail as 0 and pass as 1, and likewise, right? So step 1 here is you need to do, because this is XGBoost gradient, right? So the initial prediction, you will have to do a logistic regression over here, and that's done through partial derivatives, first order derivative and second order derivative, to get the predictions updated. So over here, you take an initial prediction of 0.5. As you can see, the initial prediction is 0.5. So you update all 0.5s here. So the hours is 2. Your prediction is 0.5. And then you do a first order derivative for getting the first grad. And the formula for that is derivative of L over derivative of P is equal to P minus Y divided by P into 1 minus P, right? Where P here is nothing but the prediction, which is 0.5. Y is the value, which is either it's Y is equal to fail or Y is equal to pass. And then you do the math, you will get, if y is equal to 0, which is fail, you get the value of 2. So wherever you see fail, you put a value of 2, and wherever you see a pass, you put a value of minus 2, right? And that's based on this. So there's a typo here. This should actually, this should be 2, sorry, it should be 2, minus 2, 2, and minus 2. Yeah, there's a mistake here. All right. Cool. So once that is done, you finish off this, and then you have the step 3, right, where you will have to split the tree. There's a split condition. So this is another rule methodology, very similar to what we saw in the previous slide. Here you'll have to update using the rules, right? So split at 3, which basically means that someone who studied 3 hours, right, what happens to that person? So if someone is less than or equal to 3, then substitute the value as minus 0.4, and if it's greater than 3, substitute as 0.4. That's how it is done. So the updated prediction, again, the learning rate is 0.1, which means that minus 0.4 into 0.1 becomes minus 0.04. And so basically this is what I'm doing, right? Minus 0.4 into 0.1 becomes minus 0.04, likewise, right? So you have the old value, which is 0.5. You come take it from here, you update it with minus 0.4. You multiply this, you get the new value, right? So basically the new prediction is nothing but old prediction plus learning rate into tree prediction, right? That gives you this answer. So basically that's what the new prediction will look like when it comes to XGBoost, right? There's another one which is called light GBM, which is leaf-wise boosting prediction, right? Again, this is another enhanced model. Previously what we did is we did tree-wise, but over here we'll do tree-wise and leaf-wise and sequential. And this is gradient-based sampling. So that's another key innovation, which is called GOSS, which is called gradient-based one-site sampling, right? Again, you can read through this. The objective is maintain accuracy, gives you faster stuff and things like that, right? So the question you may ask is, there are 4 things that we saw, right? We saw the initial decision tree, then we saw the random forest, we saw XGBoost, we saw gradient, and we did see light GBM as well. So what are the differences, right? So this is a summary, right? So if you have a small data set, go for decision tree. If you have medium, then go for random forest. And if you have a large and a very large, then you go for these, right? And then depending on what your criteria is, you can select one among these tree-based algorithms. So that's it for today. Any questions, let me know. Thank you.